Here we go. Everybody have a good holiday break? We already had a break. That's kind of nice, I guess. Yeah, I had an unusual break. See, we had class on Wednesday, right, last week? And so it came on Thursday. Thursday was my birthday. And yeah, thanks. It was not a good birthday. I got a call from my wife, and she was the vet with our dog. And so I had to leave school and go put my dog down on my birthday, which was not a good thing, you know? Yeah. Anyone who's ever had to put a dog down, you know what I'm talking about, right? It's like dogs are better than people, like in most of the time, right? So, anyways, it was tough. But so the weekend was more of like just looking at bowls and like, you know, doing all that grieving with my wife. So it's kind of a shitty break, but you know, getting back to normal. So. But everyone else was like, yeah, I had a great weekend, and yeah, Labor Day was awesome, and all this. So like, good for you. All right, so I'm just wasting time here. 11 o'clock. We have a test that's supposed to be due a week from today, right? So I don't think we're going to get through all of the material needed to do the entire test. So I'm either going to trim one problem off or extend it one additional day, which would actually give you the weekend. I think I'm leaning more towards the latter of just extending it, all right? You should, at this point, have looked at a few of the problems. You can do at least, what, how many of them? You've done two? I was going to say probably about the first one you should be able to do, the second one you should be able to do. Yeah, that one technically you should be able to do. And this is where things, 4 and 5, not really, and 6. But that's what we're here for today. So let's see how things go. All right, you ready? 11 o'clock, I'm recording, I'm not muted. Any questions before I begin? No questions?
Was there a made-up word on the exam?
Pardon?
Why was there a made-up word on the exam?
What made-up word?
Parallelepiped or whatever?
Oh, parallelepiped.
Parallelepiped?
Yeah, that's a real word.
All right.
Yeah.
I don't believe you.
You don't believe me? Yeah, look it up. I know when the first time I ever heard it, I was like, what? Parallelepiped? What the hell's a parallelepiped? Well, yeah, that's what it is. Like a shoebox. You can like tilt it over. It's parallelepiped. All right, so last class we were talking about dot product, right? And I'm not going to go through all this. We need to start like, you know, getting the pace going here, getting the train moving. And so I went through, gave you that very important formula. Where is it? I think I passed it already. I gave you the definition of the dot product, both in 2 and 3-dimensional space, properties of the dot product, and there was the formula, the big theorem, right? And this ties together how the dot product is somehow connected with the magnitude of the two vectors and the angle between the two vectors. And this more discussion about that. This talked about if the dot product is positive, that means you have an acute angle. If the dot product is negative, you have an obtuse angle. If the dot product is 0, they're perpendicular, or what's the other word? Orthogonal, right? That was huge, right? And I think that's about where we left off, right? So I don't think I did any of these examples. So let's just run through these quickly. So let's say that I give you a vector v. I tell you its magnitude is 7. Vector u, the magnitude is 3. The angle between them is 31 degrees. Find the dot product. This is just, hey, use the formula, right? You're trying to find u dot v. I'm going to use magnitude of u. Oops. Doesn't matter what order that's in, but I'll follow the formula. Magnitude of u times magnitude of v times cosine of the angle between them. So I'm using the theorem. Magnitude of u is 3 times magnitude of v is 7, and then cosine of 31 degrees. And whatever that is, you just get your calculator, right? Okay, that's it. That's all I'm going to do for that. There's nothing else involved there. This is just showing you that to get a dot product, you either need, right, the vectors themselves, so you can just multiply and add using the basic formula, or you need their magnitudes and the angle between them. It's one or the other to get the dot product. That's helpful on number 1 and on number 2 for your take-home test. All right, this one, example 4 is asking whether or not these vectors are orthogonal. So how do you check to see if they're orthogonal? Take the dot product, right? Just dot them up. So what would, can I do v dot u instead of u dot v? Do these give me the same answer? Yes. Okay, so what is it? Let's just practice because it's been the whole weekend. You all had fun, I didn't. What was it? 6, 2 times 6, and then we add to that 4 times -3. And that gives us? Yeah, 0, right? Are they orthogonal? Yes, those are orthogonal vectors. Nice, right? Such an easy way to check if two vectors are perpendicular to one another. So the answer is yes. For example 5, oops, I forgot to hit this. For example 5, I give you a u and I give you a v, and these are both in 3-dimensional space, right? These vectors live in 3-dimensional space. And I'm asking you to find the value of a. Is there not? I thought there was a straight edge in here. There's not a straight edge on the board over there? No? I'll go steal one from another room. Oh, there it is. Yes. Thank you. I didn't see it there. So we have two vectors, right? One of them is defined explicitly, right? 2, -2, 6. The other one has a variable expression in it, right? So it can be a lot of different things. Infinite number of values that a can take on. So we're being asked to find the value of a such that these two vectors would be orthogonal to one another, right? So I give you a vector that can't change, and I give you a vector that somehow we can adjust it a little bit by changing a, and I want to see how we need to define a to make these two vectors orthogonal. Well, what should I do? Dot product, right? What do we need, right? Right? To make them orthogonal, what we need, u dot v to be equal to 0, right? But that implies that when I take 2, -2, 6, and I dot that with a, 3a, -2a, that must equal 0, right? That's the implication there. Sorry, this is an implies symbol. That looked terrible. Implies means, if this is true, then this would have to be true. And now I dot them. This gives me what? 2a. I'm just multiplying first the x components, adding to it the multiplication of the y components. So that's what? -6a. And then here, this is -12a. That must equal 0. Do you all agree? Yes, and what does that come out to be? -16a must be 0, which means that a must be 0, right? In order for this to work. But all of that implies what? That our vector v must be the vector what? 0, 0, 0, right? Which means that it's the 0 vector, right? It's the 0 vector. So I want you to think about this problem for a second. I gave you a vector, right? This one right here, I gave you a vector. And we were trying to find a vector that was orthogonal to it, right? Kind of, yes? And we're saying that the only vector that's orthogonal to this is the 0 vector, right? Which isn't true, right? Shouldn't there be an infinite number of answers? But see, the reason we're not getting an infinite number of answers is what? Why are we not getting all these vectors that go around that are orthogonal to this? Why are we not getting that? No? I mean, because if I give you a vector, aren't there an infinite number of vectors that are orthogonal to it? So why are we saying the only one that can be orthogonal is the 0 vector? Yeah, it's the conditions of that vector. I'm not just saying any vector. I'm not saying go find me any vector. I'm saying the vector that you need to find has to satisfy these conditions. And there's no vector that satisfies those conditions that are orthogonal to this. The only one that works is this one. So it's not it should make a little more sense in terms of keeping in mind those conditions have to be met. All right. If this was just like any vector, then there would be an infinite number of answers, right? Infinite. So I just want to make sure you're like making the distinction between whether or not that v was arbitrary versus whether or not it had to satisfy something.
Sir,
Yes.
isn't the definition or one of the requirements of that equation say that it has to be a non-zero vector? So doesn't this mean that it isn't orthogonal at all?
Isn't the definition of what?
Like the vector u times vector v equals the was that the distance of vector u times the distance of vector v times cosine.
Of the angle between them?
Yeah,
What-
it says that they're orthogonal. I wish I wrote the definition. It's like they're orthogonal. If one of the vectors is a non-zero vector.
Okay, so the zero vector is orthogonal to all vectors, right? The zero vector dotted with any vector gives you 0. Therefore, the zero vector is orthogonal to all vectors. But geometrically, that doesn't really make a whole lot of sense to us, right? Because the zero vector is like a point, almost, right?
Yeah.
So that's a very unique situation. So we don't have a requirement that in order to use that, when you define dot product, that one of them has to be, or that they both have to be non-zero. Okay, this right here is just the formula that we just had, okay, for the dot product. The theorem, sorry. The theorem we had for dot product. If I asked you to solve this for theta, right? Solve this for theta, what would you do? Probably divide these out, right? So I divide those out, put those over here, magnitude of u, magnitude of v, right? That would get rid of them over here. And then, so now Andy, this theorem, right? This particular one would not work if one of these was a zero vector, right? Like this would not be defined. So there are conditions on the theorem, but not on just the definition of dot product. Okay, so yes? And then now what? At this point to get theta? Inverse cosine, right? And that gives you this. So that's just a nice condensed formula for finding the angle between two vectors. All right, so let's do one of these. Let's see, find the angle between those. Let's do, we're skipping 6 and 7. We're going to go straight to 8. We're going to just go right to the frying pan. So I want you to read this. And then I want us to take a second to appreciate the challenge this problem presents without vectors, without the whole idea of dot product. How challenging this problem would be. The vertices or corner points of a triangle in three-dimensional space are given. So I'll give you 3 points. Boom, boom, boom. 3 points in three-dimensional space. Those 3 points form a triangle. The question is that a right triangle? Right? Is that a right triangle? That would be extremely hard to do without this idea of vectors and dot products. So let me draw a picture first. I have my 3 points, right? I could go and there's 1, and then there's 2, and then there's 3, right? Yes?
Basically, it just comes down to if any of those 2 points are, those 2 vectors are orthogonal, right?
Yeah, we just need to check for a right triangle. We just need one of the angles to be 90 degrees, right? Or perpendicular or orthogonal. So let me draw it first. I'm going to draw it over here. Okay, this is going to be a very nice detailed picture, three-dimensional picture of these points in space. Ready? Thank you. And it forms a triangle, right, like this. And then I have the point 1, -3, -2, completely arbitrary. I get to choose these. Why do I get to choose these and position them how I want and not care? That's right, because I'm in charge. Because if I draw a triangle in here, right, your viewpoint can be anywhere, right? Like if you draw a triangle, You looking at it from where you are is going to look different than you and different from someone up there, right? So however I draw it is fine. There's no perspective we have to use. If we're on a flat sheet of paper, then most of the time we're kind of like, all right, we're going to draw it where this is X and this is Y, and we're kind of all looking at it from here, right? So we want to make sure we draw things correctly. Here it doesn't matter, right? It's like you could spin it around. So y'all happy with my picture? Yeah. Pretty impressive? All right, so what I'm going to do is start checking these angles, right? And see if any of these are right angles. Now, one thing I could do is I could call this theta, right? And then I could go try and find theta using the formula I just gave you, right? Theta was cosine inverse of u dot v over the magnitude of u times magnitude of v, right? That formula. But it'd be better if I just dot product the vectors and checked for 0, right? If I dot product and get 0, I know I've got a right triangle. But the important thing is you have to do the dot product of the what? The vectors. And what have we been given? Points. Points aren't vectors. We have to create vectors first. Right? We have to create the vectors first. So I'm going to start by checking. Let's check this angle right here. So I need to create the vector that goes from here to here. I'm going to call that v. And the vector that goes from here to here, I'm going to call that u. All right, now we got to go back to a class ago. One class, I think it was one class, where we said, how do you define a vector between 2 points? If you go from one point to the other, how do you define that vector? So v would be the vector. It would have 3 components. First component would be -1. How are you getting that? You're doing 1 minus 2, right? Because we're going from here to here. So take the 1, subtract the 2, you get -1, and then -3, and then -6. Do you all agree that's the vector v? Going from here to here. Okay, now we need the vector u that goes from here to here. So we'll do the same thing. I'm going to do this minus this one, this minus this one, this minus this one. That'll be the vector u. So -8, -2, -9, right? It's important that I'm going from here to here, right?
So
Yes.
if you go backwards to get this one.
If you did it the other way, then it would be this angle, right? So it would be a little different. Because when we do that angle, it's always tail to tail. The 2 vectors are being moved tail to tail. So if you accidentally flip this over, you're actually trying to find tail to tail would be like this, right? It would be that one flipped, and now you're looking at that angle instead. Now, it would, if it's a right angle, it would still give you a dot product of 0, though, right?
Yeah.
Okay. But geometrically, it's not the same thing, same vector. It's parallel, though. Not 0. So y'all dot this real quick, right? You dot. So if we do v dot u equals, okay, multiply here, we get 8. Multiply these, you get 6. Multiply those, yeah, this isn't happening, right? 54? It's not happening. It's not 0, right? We need it to be 0. Did I multiply that right? Yeah. Okay. So it's not 0. So you know that this is not a right angle, right? Unfortunately, we have to check 2 more, right? Which means we need vectors for those as well. So how about, let's try and check this angle. Let me call this one alpha, so we don't confuse it verbally. So if I want to check for the angle alpha, I need a vector that goes from here to here, and then also from here to here. Can I use negative v? Sure. Right? Go from here to here. Can I just flip v around, which would be negative v? Yes.
It didn't matter for this calculation, but for the v vector on the left side, the 1 is negative, or the 1 is supposed to be positive.
Because you're doing 1, unless I wrote the point down wrong. No, because you're doing this minus this, this minus this.
Oh, my bad.
No, that's all right.
Oh, I see.
But I mean, yeah, I make mistakes up here, so if I do something stupid, y'all just tell me, you know. All right, so y'all ready to check alpha? Yes, sir. Alpha, so for alpha, let me relabel. I'm going to use a different color. I'm going to go the vector Like if it were me doing this, I would just draw a new triangle and start, but I'm going to try and squeeze it all together here. So here, that vector is going to be negative v. And let's just do the vector goes from here to here. Let's call that w. All right, so negative v is just v flipped, right? So change the signs. That's negative v. So 1, 3, 6. And then w, let's see. W is, hold on, no one reply. Let's see. Let's, I didn't pass out the attendance last time, did I? I think I was like, Cal 3, you should just be here. Here we go. Here, why don't y'all sign in? And if you were here last time, go ahead and sign in there as well. There you go, thank you. Volunteers, we'll take volunteers, and then you can only play once, and then until we go through everyone. So who wants to give me W? Who got it? Okay. What do you got?
The last one wrong, but it's -7.
Negative 7.
Then +1.
Positive 1.
And then -3.
Negative 3. Good. Good. Everyone got that? Okay. So all I did to the vector, the red vector going from here to here, I just flipped a v over, so negative v, that's there, and then here's w from here to here, and that's that vector. Now dot them. Is it 0?
No.
It's not? Damn it. Okay. I was hoping it would be. Negative v dotted with w is -7 plus 3 minus 18. Yeah, not 0. We're starting to run out of chances here, right? We need it to be 0 to get a right angle. One more. What could I dot together? Who wants to volunteer to tell me what two vectors I could dot together to check that last angle beta? Oh, so you're, all right, so that's, yeah, you're out. All right. Negative u and negative w, right? So that one flipped and that one flipped. If we dot those two, sorry, I'm doing cross product. That's coming later, sorry. If we dot the two together, then we will get hopefully 0, maybe not. So negative w, here's w, right? Negative w, I'm changing the signs. And what was it, negative u? I think I've erased that. What was u? Someone help me out. Or someone tell me what negative u is. 8, -2, 9. Do we all have agreement on that? 8, 2, 9. Everyone agree? Okay. So that's this one flipped, and then that one flipped as well. So we dot those. What do we get? Do we get 0? No. No. Okay. So we dot those, they're not 0. Which means this triangle is not a right triangle. Yes?
Is our W vector right? I thought in order to find the vector, it's the head minus the tail.
Yes?
Oh, I hit it wrong again.
Well, that's why I want to go through this, because this is the most common mistake students make, is finding vectors from one point to the other. They'll either do it backwards or get signs mixed up, right? You just, do enough of it, you'll stop making those little mistakes. All right, let's move on. Okay, projections. So this is actually something that's going to be extremely useful to us. Vector projections. So I want you to take a look at this visual. Wait, don't look yet. I should have refreshed this. There we go. All right, so what we have here are two vectors, a red vector and a blue vector. Now, remember, those vectors could live anywhere, right? They can move them around, but I put them tail to tail. Tail to tail. Of course, there's an angle between them, right? What you're looking at here in this purplish looking thing here is what we call the projection of the blue onto the red, right? The projection of the blue onto the red. And all it is if you were to come into the red one here with like an orthogonal, like perpendicular, and you were to go until where you hit the tip of the blue one, from there to there, that would be your what we call the projection vector. It would be the projection of the blue onto the red. Make sense? It's like in other classes, we call this dropping a perpendicular. You're going from the tip of this and you're dropping a perpendicular straight down to the red. This purple is a vector, okay? So the projection of the blue onto the red gives you a vector. Can anyone tell me something about this purple vector in its relationship to the red one? What's the relationship between the purple and the red? Like, they're parallel, right? They're parallel, which means that the purple one should be a scalar multiple of this red one, yes? A scalar multiple. That's just us just looking like if it's pointing in the same direction, it's parallel, right? Which means it's a scalar multiple, all right? Now, we'll get into how we find this. Okay, there's a formula to find that vector. But what if I changed the problem around and I said, right now, let me make my red one longer. What if I said, okay, I want you to project the red one onto the blue one instead. Not the blue onto the red, but the red onto the blue.
You would make it perpendicular.
Yeah, you have to make it. So right now, here's where we are, right? We made a perpendicular, right, like this, drop down, and that was our projection vector. But now I want to project the red onto the blue, and what's kind of a trouble part of that? The blue's not long enough, right? It's like you want to drop a perpendicular, but the blue's not out here, right? It's okay. That just means our projection vector is going to be longer than the blue one. So it's going to look like this. I'm going to try and project the red onto the blue, right? There's the projection vector. And you can see that it still is dropping a perpendicular to this imaginary line that goes through the blue, and then drop the perpendicular and create the vector that goes from here to here. Do you see that purple vector is still a scalar multiple of that blue one? Okay. What about this? I'll make it a little easier to see. What would the projection of the red onto the blue be here? Do y'all see the projection of the red onto the blue? No? Okay, so we're going to try and project this onto this blue vector. So we're just going to kind of draw a line through the blue vector and then drop a perpendicular, which means it's going to be here, right? It's going to go from here to here. It's just going to point backwards. You see? Red onto blue. There we go. Are these two vectors parallel?
Yes.
Yes, remember, parallel vectors means scalar multiple. That's all it means. They don't have to point in the same direction. So those are parallel vectors still. So that purple is a scalar multiple of that. All right? Okay, so that's the vector projection idea. And of course, this would work in three-dimensional space as well. It's just easier to see it on a flat sheet of paper. Any questions on it? Okay, how do we calculate it? Well, here's the formula for it. First, the notation. If you want to project the vector u onto the vector v, here's the notation for it. PROJ, projection. This is the vector u. You are projecting it onto the vector v. So the one that is subscripted down on the bottom is the one you're projecting onto. All right? This vector is the one that you're projecting down. Now, the calculation for this is this right here. This is the actual, this is the formula. If you want to say you like formulas, this is it. Didn't we say it was going to be a scalar multiple of the vector it was being projected down onto? Right? Scalar multiple. So if I'm projecting u onto v, then my answer should be a scalar multiple of v. Right? A scalar multiple of v. Here's v. That's the vector v. This right here, is that a number or a vector? I'm having a good semester. I'm having a good semester. I'm over 500 on my markers. Okay. And I haven't hit any students. So it's, Is that a vector or a number?
Number.
Number, why?
Because you got vector dot vector, which gives you a number, and you got vector dot vector on the bottom, which also gives you a number. So you got a number over a number.
Yeah, this dot is a number, right? And then this is magnitude, length of a vector, which should be a number, and then squaring it's a number. That's also, you can look at that as a dot as well. But okay, so this is a number, right? So this is a scalar multiple of v, which is what I said. The projection is just some scalar multiple of the vector you're projecting onto. And that is the scalar exactly, all right? Now, I'm not showing you why, I'm just showing you the formula, all right? So that's it. All right, now, there's a difference between the vector, the projection, and what's called the component of u onto v. It's a different notation. The component of u onto v. I'll explain what it is in a second, but here's the formula for it. It's v dot u over the magnitude of v. Is that a number or is that a vector? This is just a number, right? This is just a number. That dot product is a number. The magnitude of v is a number. So what is the component? What is the component of u onto v, also called the scalar projection? For those of you who might see that in a different class. What is it? It's just the length of the vector projection. So I'm going to go back to my picture. All right. This purple vector is the projection. Let's call this one u. Let's call this one v. All right. This vector right here, the vector that you're looking at, is the projection of u onto v, right? That's this vector. The magnitude of that vector, the magnitude, the length of that vector, is what we call the component of u onto v, all right? It's just the length of the vector. So that gives you a vector. This gives you its length. All right, I'm going to jot those formulas down so that I don't have to refer back to them. Okay, I'll put them over here. So the projection of u onto v is going to be what? U dot v over the magnitude of v squared times v itself, right? And then the component of this, the formula is actually a little bit easier, right? It's just u dot v over magnitude of v. Which one of these? Let's do 10. I feel like we should do a three-dimensional vector. No, let's just do 2. We'll keep it simple. This is just computational. All right, so find the projection of v onto u. Look, v onto u, not u onto v. You'll see I switched them.